everyone for being here for this mini course. First of all, Mark, for accepting our invitation to deliver the mini course, and thank you everyone online to be with us on Zoom. So, just a few words to introduce Mark. Mark Iwen is an outstanding professor and expert in computational harmonic analysis, mathematics with data science, with applications to signal processing. He got his PhD from the University of Michigan, Ann Arbor, and then he did postdoc in the University of Minnesota, Duke University, and he now holds a dual appointment at the Department of Mathematics and Department of Computational Mathematics and Computer Science and Engineering, I believe.
Science and Engineering.
Science and Engineering, sorry, at Michigan State University. So Mark did a lot of work in compressed sensing, sublinear-time algorithms that he will explain to us in these 3 days. More recently, also in the field of high-dimensional approximation. So personally, I'm really excited about this mini course. I think we'll learn a lot from Mark. So about the logistics, we'll have 2 sessions. So the first hour of mini course will be from now to 3 p.m. Then we'll have a quick break, 15 minutes. We'll resume at 3:15 up to 4:15, and then we'll have a Q&A. But I think if people want to ask questions before, you can either raise your hand if you're here, or you can virtually raise your hand on Zoom, and you will be given the opportunity to ask a question live. Yeah, with that, thank you again, Mark, and the floor is yours.
Yeah, I encourage people to ask questions whenever they might arise. I will probably confuse you fairly often, not because what I'm talking about is difficult, but because it's me talking about it. So when that happens, just get the clarification you need, and we should all be able to go on. So just a little bit more in detail about what the courses are going to be about here. I'm going to talk about a couple of sort of interdisciplinary approaches for compressive sensing. So the first couple days are going to be devoted roughly to maybe this. So compressive sensing the computer science way, plus a little bit of Fourier analysis, is going to lead to sparse Fourier transform algorithms. So I'll tell you what that means in a second. So that should be SFT when I say SFT algorithms a lot in the future. So what are these? These are compressive sensing algorithms tuned to the Fourier basis that run in sublinear time. So in other words, the total number of samples and the runtime better than the number of basis elements that you want to try to perform your approximation in. Okay, so and sort of the specific way, there are many ways of coming up with these things. This specific formula that I'm going to sort of give you maybe has a distinction of allowing for entirely deterministic algorithms with near optimal compressive sensing approximation theoretic guarantees. And also allows you to take these things to handle the multidimensional Fourier basis. So you can do things like approximation of functions of many variables in the Fourier basis very quickly with these types of methods. So a little bit of bibliography here, because I'm going to be woefully inadequate with respect to giving people the credit they deserve for the ideas that I'm going to be doing here. So if you want to see what a lot of what I'm talking about today and tomorrow, where it comes from, you can Google the following terms. So these come from heavy hitters algorithms primarily. This is from the streaming algorithms literature. Okay, in computer science, you can also maybe find combinatorial compressive sensing as a keyword that'll bring some things up. And this work is going to be my remixed version of songs originally composed by folks like Muthu Krishnan, There's Martin Strauss, Anna Gilbert. Who else? Graham Cormode. Piotr Indyk, and a whole bunch of other folks that I am going to neglect saying, many people, right? So I'm remixing ideas from this literature by a lot of these folks here. And what I mean by the Fourier analysis methods, again, to sort of give credit where credit is due here. What I mean here, there are, these involve ideas from unequally spaced sparse Fourier transform techniques. So, and rank one lattice techniques for functions of high dimensions, things like this. And you can read about these types of ideas in a nice book I'll reference later by Daniel Potts. Other authors are Stiedel, Ash, Plonka, Carolyn Plonka as well. Vladimir Rocklin has worked a lot on this type of stuff. Dr. Rocklin being one of the influential unequally spaced sparse Fourier transform methods we'll sort of interact with, at least the ideas a little bit. Okay, so this is going to be sort of what we're going to be talking about the next couple days. And then maybe the third day will be dedicated to sort of a second pseudo formula here, which is going to be compressive sensing done the more traditional or mathematical way, I should say. So compressive sensing the math way. Plus SFTs, the computer science way, if you like. I'll say what I mean by that in a second. Are going to allow for SFT techniques, so sparse approximation techniques that run in sublinear time for more general orthonormal bases. So SFTs for more general bases. Not too much more general, but at least more general orthonormal bases for functions of many variables that you can also do compressive sensing with respect to using the following types of techniques. So here you can interact with things like the restricted isometry property for compressive sensing that matrices need to have in order to have success. Algorithms like COSAMP, I'm going to focus on quite a bit by Needell and Trapp, and dimension incremental support identification ideas. Again, sort of by Daniel Potts, Lutz Kammerer, and a bunch of folks from that area. So these are, Tao, Candes, Donoho. I feel like the Trapp and Needell feel like I need to reference these folks a little bit less. They're probably quite a bit better known to most people who are in the room, right? And so sparse Fourier transforms the computer science way. What does that mean? Effectively, I consider this to be sort of Monte Carlo integration schemes that are sort of layered, which allow you to figure out which basis elements have heavy coefficients, heavy Fourier coefficients. And that's a lot of what the sort of, again, first sublinear time Fourier algorithms by people like Anna Gilbert again, Martin Strauss, Piotr Indyk, and others are based on. And when you combine those ideas with sort of recognizing that the restricted isometry property lets you give sort of construct grids that allow for accurate Monte Carlo guarantees over entire function classes of sort of sparse signals, you can get the same types of deterministic guarantees and things like that for more general bases using these ideas and sort of mixing them together. So this is what I'm going to be talking about here. And I should say that a lot of this stuff is going to be summarized in the lecture notes that, again, Craig and another graduate student of mine have written up that you can find on my website if you want to see some detailed proofs of things that I don't have time to do. So you can look at chapter 6 of a mathematical introduction to fast and memory efficient . 6. Thank you. Yes, that is the perfect type of question. Often my hand and brain don't communicate very well. Yep, algorithms for big data. And these are just lecture notes on my personal webpage, which are riddled with errors, not sourced properly at all. The references it needs a lot of work, but nonetheless, the basic ideas about stuff are there, and perhaps it will continue to improve with time, should anyone be interested. Okay, good. So given this, hopefully that's sort of background material for anything you're interested in learning a little bit more about. And with that, maybe let's remind ourselves what compressive sensing is in the first place and sort of what the problem is that we can now talk about solving in the computer science way to begin with. So compressive sensing mainly as a means for me to fix some notation, make sure that we have some general sense of what I'm going to be writing on the board. All right, so I'm going to take a matrix M, which I will uncreatively, call M because it's a matrix. It's going to be rectangular with many fewer rows than columns. And I'm going to have some measurements of an arbitrary vector from this matrix for some x that I want to try to recover from these measurements, right? So you want to, given this information, recover x, right? So I simply want to invert this linear system. It's pretty simple. Problem is, M is much smaller than N, so I clearly can't do this. So we assume that we have some sort of sparsity. So since we can't do this in general, we are going to solve it for a restricted class of X, which are vectors that have a small number of non-zero entries, right? So in other words, I'll take this L0 norm and say it's less than or equal to S, where S is less than or equal to M, which is much smaller than N, right? Now I have a chance of being able to do this. Yep.
X in CL, right?
Ah, yes. Thank you. Thank you. Yep, exactly. And okay, if X is exactly S sparse, that actually turns out to be a fairly easy thing to do. So what you more generally would like to do is be able to do this for any approximately sparse function. So more generally, we will assume that X is approximately S sparse. And then we have to define what that means, right? So let me fix some sort of common notation here to describe what that means. So Probably you've seen this in some papers if you've read this stuff before. So I will work with respect to this sigma 1 definition of the best S-term approximation error for a given vector x. So S here is going to be an element of the set bracket n, and this is just my way of talking about integers from 0 to n minus 1. That's supposed to be a z. And x is whatever vector you're interested in, in high dimensional space. And this is going to be defined then to be the minimum over all choices of subsets of n, where the cardinality of S, this is a subset S, is less than or equal to little s. So, right, of the one norm between x and x sub s. So what is x sub s? This is clearly going to be, so this is x restricted to s, I should say. That's the set S. And okay, so what is this stuff? This is sort of what you might expect it to be. This is a vector whose jth entry is equal to the entry of x if j is in the set S and 0 otherwise. So it's just a mask, right? We're zeroing out all the entries of x that aren't in S. So we go look, that should probably be an infimum instead of a minimum, but or maybe anyways. Right, you go ahead and look for all of the best possible approximations, just picking out a small number of entries, and that's the minimum error that you can get for this particular vector.
Hey,
So,
Mark, it's Ben Adcock here, remotely. Should it be small s on the left rather than big S?
this is on the left. This is a small s. Sorry,
Yeah.
I probably shouldn't have used two s's.
Right? Yeah, my resolution's not good, so yeah, it's.
Yep. That is
thank
small
you.
s. Thank you. Thank you for getting my notation straightened out. Please continue. Yeah, exactly. So definition that I won't define 100% here, but for small s again, I'm just gonna sort of wave my hands a little bit and use x little s to be any minimizer which achieves this error. So this is a sparse version of x. So this is going to be equal to x restricted for some subset, which I could call maybe S opt. There could be more than one such subset. Order them in some way that you like and pick the first one in your order, right? Such that you actually achieve this worst case error. So I'm going to use both of these. So this is again little s. This is now little s. It's a best S term approximation to x. I just don't want to have to carry around sets too often, so I'm going to sort of use this as a way to avoid having to do that. Okay, so other things you can do, right? You can exchange the one with some other p norm and change the definition up here if you want. We're going to work with the one norm primarily. So
the second definition, there could be very many vectors, right? I mean, isn't that just the argument set?
it could be. So go ahead and take all the sets in the power set of n whose cardinality is smaller than s, less than or equal to s. Order them any way you want, lexicographically or something. It's a finite set. And then take the first one that achieves this. So there could be more than one, but we just need one.
Okay.
And So all of our error guarantees are going to be with respect to this guy. And then, that's just an irritation that makes proving things a little bit more annoying to realize that it isn't necessarily unique. This guy
It's
is
a
unique.
minimizer of that.
Yeah,
And
exactly.
it's just you fix it by fixing some order on these. Okay.
Exactly, yeah. So this guy will be unique, but it sort of doesn't matter in the error guarantees that I'll show you. So that isn't something that like makes everything false because I'm dumb. I probably did something else to make things false because I'm dumb, but not that anyways. Yeah, no, good question. Any other questions? Speaking of which, here are some questions that we have to answer. Okay, so two main things that we have to answer. So for the class of X where this best S-term approximation error is meaningfully small, because if it's too large, right, you could potentially get anything and then you can't expect very much. So where X is approximately sparse, when can you do inversion accurately? Either exactly if it's exactly S sparse, or still accurately if it's almost S sparse. So what type of M are we going to consider? That let us do this. And we sort of have answers to this that you probably, a lot of you know. So I'm going to focus and I'll be a little bit more explicit here. So that let us invert our measurements, right? When, again, being highly non-rigorous, when X is approximately sparse. So I'll put it that way. So what type of matrices let us do this fast? Because that's what we're going to need eventually in order to get the sublinear time behavior. So it's going to be a little bit different and a little bit less complete answer than what you're used to from the compressive sensing world generally. And so when inversion is possible, what are the algorithms that actually let you do this, right? So we need to know what good algorithms exist that you can implement quickly, that take your measurements and spit out a good approximation to a vector in Cn by just listing the most important entries, right? If you want this to run faster than n time, you can't output an entire vector. So we're going to always be outputting a set of entries and then coefficients, right? It's sort of operating that mode. But when represented as a big vector, it should be high quality, which means in particular, in this case, that I want to get compressive sensing type error guarantees that are sort of near optimal. So the algorithm that I'm going to talk about here gives you, and I'll give you some more details on this, sort of what you want. So you input your measurements into some algorithm A, and it very rapidly outputs an approximation to the original vector X, which in the 2 norm is going to be less than this best approximation error with respect to the 1 norm divided by the square root of S times some constant, which you can spend time figuring out a universal bound for. Yep.
Mark, so in your measurement model, there's no noise. So is that for notational convenience to kind of make the presentation easy, or because, or it could be done with noise or not?
I'll give you a theorem that involves noise later. Okay. This is mainly just to sort of point out that in the noiseless case, so no noise on the measurements, in other words, that you do want the sort of performance that you would generally prove for like a basis pursuit type method or something like that.
Okay.
Okay, the punishment that you're going to see here is that we're going to end up using more measurements than basis pursuit would use. There's generally no free lunch. So we're going to use a more structured set of measurements that ends up being larger than the smallest set of measurements that would work for basis pursuit. And then we're going to use those extra samples to radically speed up the runtime of the method. That's sort of what the general formula is. You have way more notes than I need or something. All right, good. All right, so let me go ahead and answer this first question right here. what type of X I can use, or what type of matrix I can use. Here's an answer to question 1. This is in no means the only answer. I would be interested in better answers. So you can use a sort of matrix with a restricted type of coherence guarantee to make all of this stuff work ultimately. So everything we talk about here is going to be based on choosing a couple integers, our bracket n set again. I'm then going to want a matrix M, right, M by n. So I want to have a small number of rows as usual, and I want it to have something that I'll call K alpha coherence. So, and it's going to have this property if 2 things hold. So first of all, every column of M has to have at least K ones in it. And so let me specify this a little bit more. I'm going to make this highly restricted. In fact, these are going to be matrices of 0s and 1s. So let me not obscure that fact, right? So I'm going to need a matrix of 0s and 1s where every column has at least K1s in it. So I have to have some 1s in every column, in fact, a potentially large number. And I need to pack them in there very carefully because I also want to have all of the column inner products to be small, so bounded by this alpha parameter. So also, I'm going to need that the jth and lth row of M are always less than or equal to alpha whenever L is not equal to J. And this notation is, this is the jth column of my matrix. Right. So, and what we're going to see is that for any matrix like this that has this highly, pretty structured setup, there's going to be a sublinear time inversion algorithm for anything like this. Okay, so that's one thing we can say. So there's a sublinear time recovery algorithm sort of answering this question, and I'll write it down. There's one, at least one, that does number 2 right over here for any such K alpha coherent M. Okay, so that's sort of what we want to see next. And so the next thing I'm going to do is I'm going to tell you what the reconstruction algorithm is, and then I'll talk about why it works for a while afterwards. So we'll get to the punchline sort of quickly. So before I can tell you what the algorithm looks like, though, I need to have one little definition of another submatrix of any such M that's going to show up in the algorithm, and then that's it. Otherwise, the algorithm is really easy. Yep.
Can I just ask a more general question that I sometimes don't understand in compressed sensing? The matrix M, how much do you get to choose M, or how much is it given? Is the question clear?
In this case, we're going to be designing these M are going to have loads of structure. We're going to have to design these guys. I think it would be highly odd that you would accidentally get an M like this that happens to work. However, probably tomorrow you'll see that you can design M like this that work really well with respect to sparsity and the Fourier basis that are very natural, and that sort of lead to natural types of grids that you might want to use for, doing approximation with respect to trigonometric polynomials. So tons of implied structure, but it interacts nicely with some really important bases and lets nice things happen. So there is a reason to continue following the structure, I guess. Yeah.
When you write sublinear-time algorithm as number 2, do you mean like it answers question 2, like it'll bake that down?
Yeah, exactly. Yep. And so it'll have this type of error guarantee, and it'll run in sublinear time. Yep, perfect. Okay. I like the questions. Keep me honest, or at least lying well. Yeah.
Another quick one. So the coherence usually, okay, now you're in 0, 1, to the n times n. Usually, like there's an assumption like the columns are L2 normalized. So it normalization here. Okay, of course.
You'll have to normalize later.
Okay. there
Yeah.
will be- okay.
So the actual, yeah, you'll end up sort of implicitly normalizing later. I told you, no optimization. I'll turn around, you can sneak out while I'm writing on the board. Anyway, so let me define one more thing, and then I'll sort of write down what this algorithm is, and it's super simple. So if you don't understand what the algorithm means, it's because I've done a bad job, and you should make me do a better job. Okay, so if I have some matrix with zeros and ones, that's K alpha coherent, or maybe not, I suppose it doesn't even matter. And you give me some choice of n that you're interested in. So a number from the column index. Okay. Then I'm gonna have to talk about at least a little bit about a submatrix of M called M operating on n. I'll just call it this. So what is this? This is a K by n matrix. So I guess we do want M to have at least K ones in every column. You'll see in a second when I define this. So not just this, but it should be K alpha coherent, I suppose, or at least have enough ones in every column. So this is the first capital K rows of M containing a 1 in the nth column. Okay, so every column has at least K ones. So for the nth one, you look in that column, find the first K rows with a 1 in it, pull out those rows, that's your submatrix. Okay, so what that means, so I'll put it over here. Pictorially, what this matrix is always going to look like, and it's part of why this algorithm I'm about to write down works. It is going to be, right, still a long matrix. The nth column is going to be the ones vector, right? So this is just the vector of all ones. And then all of here, it's going to be very sparse. So a lot of zeros. And why is that? There are going to be a lot of zeros there because if I look in this column, right, the inner product of these two columns has to be small. And all the entries are positive, in fact, 0 and 1. So there can be at most alpha 1s in this column, or else I would have broken my inner product condition over here. This is a submatrix of the original matrix, right? So there can't be too many 1s in any of these columns, is sort of what you get from this coherence condition, right? So that's what this submatrix has to look like. Which is going to sort of drive why this simple algorithm is going to work that I'm going to write down here. All right, so let me go ahead, and this is a heavy hitters algorithm, effectively from the computer science universe, more or less, right? So I'll call this median recovery. So this is my answer to the second problem, and this is going to be an algorithm if you want to write it as a function, I guess, right? It is going to take a set of measurements it'll take, this is the power set. It's going to take a support set where you think the most important entries are. The support set could be all of the potential entries, right? In other words, you supplied no additional information. This just gives you the possibility of making your life a little easier. So this is a subset of n. These are our measurements. We're going to need our matrix. It has low coherence. And given this information, we'll then output some good approximation that satisfies the type of error guarantee that we saw before. Okay, so that's what this guy is. So given, all right, mx, which means I'm also assuming we actually know what m is, some subset capital S of n, and a sparsity that's at most half of the cardinality of this set S. Otherwise, you don't have anything to do, right? Because apparently you know where the support is already. So what we're going to do, super simple. For each n in our potential support set, we're going to go ahead and estimate a coefficient in the following sort of ridiculous way. So I'm going to just take, I'm going to estimate the real part of the nth coefficient of the vector at position n. Okay, by simply taking the median of the entries of the real part of the submatrix that has ones in the nth column times x. All right, so this vector. I have those because this is just a submatrix of the original M, so I can find where those are and do this median. I'll do the same thing for the imaginary parts. Okay, those are going to give me my entries. Okay, when I'm done doing that, I'm then just going to sort my coefficients that I've estimated by magnitude. So I have those, so I can sort my estimates by magnitude. And then I'm going to take the corresponding entries and their n's that I've estimated and output those as my sparse approximation. So, all right, so maybe I'll give some sort of notation here, right? So Zn1 is going to be the largest one, Zn2 will be the next largest one all the way. So I'll take S tilde, that's my approximate support, to be the associated entries that were largest, down to 2S or however number I have. I guess if this is less than S, you can just output them all, right? And then I'll go ahead and output Z restricted to S tilde as a compact version of my approximation. So, and this is going to be my estimate. And I claim that it's going to be compressive sensing error guarantee accurate. Okay, so any questions about this stuff? So intuitively, maybe why should this work? All of the entries of this, if you think about what they look like due to this sort of structure, they're going to look like xn, because we're measuring the nth entry of xn with all of these guys, plus some little entries here from this very sparse other set of columns that's hitting other weird entries of X and sort of averaging them in a bunch of strange subsets. And so you're going to argue eventually that most of these epsilons are going to be small compared to the optimal error that you're interested in because of the highly structured nature of this M. That's sort of how the argument goes. And it takes some thinking to see this. I'm not saying it's obvious, but that's sort of why this thing ends up working. The proof is in those poorly cited notes that of the following theorem is in the poorly cited notes that I mentioned before. So let me just give you maybe what you can prove about this. Yep.
Is there any sort of like relative, is there like a relationship between like what K and alpha needs to be? Like if alpha is like a lot larger than K, does that maybe like mess with the sparsity?
Alpha a lot larger than K is going to be bad. So effectively, and we'll sort of tell you actually in this theorem what you end up needing here, but basically you really want to have K a lot bigger than alpha, because that's going to be something that corresponds to a non-trivially sort of incoherent matrix. And that's why it's hard, because you need to you want to have a small number of measurements. So M should be small. You don't want to just make M huge, because then you sort of failed. So with a constrained M size, you want to pack in as many ones as you possibly can, subject to not overlapping in any pair of columns, any of them enough to get this coherence bound to break. So this is, these take thought to, and I'll show you how to build some things like this. It takes some thought of things like the Chinese remainder theorem to be able to come up with examples of how you can do this. And once you see a couple, you actually realize that there's a vast literature of constructions for you already. So you can open up your favorite error correcting codes book and you'll find about 100 matrices that do this for you. These turn out to be linear error correcting code matrices give you these things. So I'll mention that a little while too. So there are many examples. It's not like there's this one. Yep.
Just a minor notational thing. So the cardinality of S tilde, is it alpha S or 2S?
It's 2S.
2S, okay.
Just for sort of technical reasons, I guess.
Yeah.
Okay, excellent. Any other questions, intuition type things? So let me sort of give you an accuracy theorem, which will also tell you how large you want K to be and related to alpha and some other stuff like that. Here's a theorem you can find in those notes. So yeah, it's a bit more complicated than it has to be, but not too bad. So I'm going to let you pick some positive number bigger than 1. It's a parameter. You got to pick a sparsity that's little s from your set here. You're going to have your vector that you hope is sparse, x. And for Simone, thank you for planting that question. You get some measurement noise you get to add on to your, to your measurement. Okay. And then you need a good measurement matrix. So we will take our highly structured 0-1 matrix and force it to be 4 alpha s plus 1 alpha coherent. All right, so now you see that K is quite a bit bigger than alpha. Right. And you have to assume, this is crucial, that you have input a set S that actually contains useful information about the vector X. And a lot of what we talk about next is going to be how to find such a set quickly. It turns out to be the hardest thing. So the set S that we input over here has to be informative. So in particular, we'll say that it contains the set of heavy elements or heavy entries. Okay, that's going to have a bunch of parameters decorating it, but CS beta. Okay, so what does this mean? These are going to be entries of X whose magnitudes of the associated entries are bigger than beta times this best S term approximation error of X with respect to S divided by S plus the infinity norm of N, say. Okay, so you need to be able to guarantee that you found me or included all of the things in S that are bigger than some averaged version of your best S term approximation error plus the worst sort of extra noise that you've dumped into any particular place. So if you can guarantee me that the set you've given me at least contains those important elements, then this median reconstruction algorithm that takes noisy entries of measurements of X, right? The measurement matrix, this set S, and your sparsity. Is that what I asked for? I think oh, yeah. Or I think I said M, whatever, right? So this guy is going to output this vector Z, and it's going to be less than some constant, some absolute constant that depends on B times the best S term approximation error divided by the one norm divided by the square root of S. Thank you. Plus the square root of S times the infinity norm of N. All right. And if you really want, you can bound this absolute constant by something. I'll just put it there because it's here. All right. So it's going to be less than this particular number for whatever choice of beta you came up with. Okay. So what does this mumbo jumbo mean? In particular, you can just think of it this way. If you give me the entire set of entries, so I'm going to estimate all of them, and then just output the biggest two estimates that I get, then this heavy element set is automatically satisfied because I gave you everything. It certainly includes these entries, right? This is a subset of N, of bracket N. So you'll achieve this best S term approximation error that I promised you when you don't have any measurement noise. So that's one way of looking at it. If, however, you have some clever way of finding a superset that's not too big of these important entries that satisfy this condition, then you only have to estimate those important entries, which is going to be faster than N time because there are a smaller number of them. And you've done everything you have to do, so you still get this error guarantee that you want, right? So that's the dynamic tension that we're playing with here. So the real goal is going to be to talk about next how to find this sort of set of heavy elements more quickly, and then employ this median recovery magnitude estimation procedure to just get their coefficients and then call your life good. Okay, so just as sort of a runtime note, the runtime of this thing, if you run through it, is going to be order of your superset size. So we want to have a small set S times the maximum of K and log of the cardinality of S. Right, so why is this? Well, this is finding a median, so you can do this in order K time with a fast median method, or at least you can believe if you use a more easy one, you can sort these and do it in K log K time, right? That is assuming, and this is crucial, that I can find the submatrix in order K time. So we have to be able to do that as well. So if Mn can be found or generated in order k time for any particular matrix M, any column of this guy, I should say. If any column of this guy. Okay, so I figure out where the rows are, where there are ones in the nth column. I have to be able to do that quickly. I form this, I do the median. That's at worst sorting time for these guys. Then I have my S of these estimates. I sort them. That's S log S time, cardinality of S log cardinality time. Pick out the largest one, spit out the answers, I'm done, right? So point is, if I have the luxury of putting in a small s, I have a sublinear time algorithm just from this thing.
Review which of these constants are God-given and which you choose and which come from the problem.
This is this is user choice. This is sparsity. It's user choice, I guess. X is God-given. N is God-given. You don't have any control over your noise. Then the S is containing this, I guess, is a God-given condition. It depends on things you don't know, but you can estimate quickly, maybe.
Is it clear how you can pick like the smallest or like small in some sense that's what you want, right?
Yeah, you want a small s. Yeah, so we'll talk a lot about how to estimate this guy. In terms of how big this set can be, you can work out that there are at most 2s elements in here. It can never have more than 2s elements in this guy. So roughly, why does that work? So this only makes things worse because it makes there be potentially fewer elements. So let's ignore the noise for a moment. Here, if you remove the s largest entries of x, which you sort of have no control over, the resulting size of what's left is going to be the best s term approximation error. And then if there are more things, more than s remaining guys who are bigger than that error divided by s, then you would violate the fact that you had a best s term approximation error of that size. So the cardinality of this guy, this doesn't tell you how to find it, but it does tell you that there are at most 2s of these guys for any of these parameter choices. So there aren't too many large entries that you need to identify. This set could be empty, and then that tells you basically that this is a bad sparse approximation problem for these parameters, and anything you output is basically going to suck. So you can output basically anything, and you'll be fine. So if it's the empty set, it means you have a hopeless problem for that parameter choice of that. No good sparse approximation. Yep.
Do you choose alpha, or is that provided somewhere?
Alpha is something that alpha is sort of a free parameter here. You basically want to come up with an alpha that minimizes m subject to this condition being true. And so we'll sort of see what you can get away with respect to alpha a little later. So it's kind of free at this point. But you know, the realities of error correcting codes mean that there are only so many things you can do trying to minimize m with your choices of alpha that make sense. Because also, there's also feedback. If you make alpha really big, then k gets bigger, and clearly m has to get bigger. So, there's any other questions about this theorem before I sort of cover it over with another? Yeah, it's not meant to. It's meant to sort of introduce you to some notion of heavy elements. Yep.
Could you clarify how we choose the capital S again?
Yeah. I haven't told you anything about that. So you don't have to know. All I'm saying is you can choose it if you want to be all of n, and you have an n log n time method, like FFT time. So it's still pretty fast. And this condition is automatically satisfied, so you can always do that. The whole trick to sublinear time algorithms going forward is going to be telling you how to do something smarter than that. That you have identified the entire problem. And the general notion, the general thing we're going to end up doing is using more samples, more measurements that let us figure out what a good S is. So our measurement setup is going to get even more structured and terrible than it currently is, but the result will let us determine a superset of this set really fast. So that's what we'll sort of talk about next. Good. Any other questions? So I've effectively run out of time.
We can take a break now if you want to add something quick that it makes sense to add now. Or
Yeah, maybe let me just add. Yeah, we could take a break now, and then I'll sort of start here next time.